I think it starts out. Yeah, I think it starts out with my content if I remember.
Right.
Or all right. So welcome to the 3146 Test 2 review. Um, this is the second time I think we have done this, but it will be the first time for you guys. So this test is going to be going over four different sort of general concepts. So we will review each one of those. Let's if you go to the next slide. Um, those topics are multi-threading, p-threads, data sharing, and CPU scheduling. So those are the four topics for the test. And if we could move on to the next slide, we'll get started with p-threads. All right. So what is a p-thread, right? So a p-thread is a structure. It's short for POSIX thread. And what it allows you to do is if you have a program that's running, you can start multiple streams of execution at the same time. So those are the threads. Um, P-threads are just a system. It's a way that a lot of Unix systems will will manage thread-based operations. So using multiple threads is called multi-threading because we have multiple paths of execution going at an individual time, and threads come off processes. So one process can have multiple threads or multiple streams of execution at a given time. When you start running the program, you start at the main function, as you do with a lot of programming languages. I'm sure uh, all of you are familiar with Java and your public static void main, all of that. Well, it's the same way in C++. So any threads that you create need to come out of the main function. So because this is quite an old system, POSIX threads have been around for a very long time. There are some kind of silly computer things that you have to handle that make your life more difficult, but p-threads need to function correctly. So if we go on to the next one, we can start going over the structure. Mohammed says this is an hour long, right? This is an hour and a half, I believe. Alyssa?
We scheduled it for an hour and a half, but last time it only took maybe an hour and 5 to 10 minutes. So it's definitely not going to be the full hour and a half.
For sure. Okay, so we'll just run over a couple different things that are fundamental to p-threads. So the first thing to do is the hash include. P-threads, if you know anything about headers in C, this just means the program knows what to do with p-threads when it sees it. Um, After that, you need to use the the dash L pthread flag. When you compile the file, you're probably doing this in AWS, so this is what you would put into the console. Lpthread is short for link pthread, so linking is the last stage of compilation. So doing these two things, or these first two steps, the including and the linking, will tell your program what it's supposed to be doing and then where the implementation of pthreads is. And that's the LP thread right there. So say you have a function and you want to actually call this function as a p thread, right? You want to create a new thread and let that run while your main thread or some other thread you create does other stuff. So there are a couple special things. As I said, it's been around for a while, so there's some technicalities that we have to deal with. So the two big ones are that a function that is going to be called by a pthread must return a void star. So that is a void pointer. Do you guys remember pointers at all? Well, I'll assume you do, and just say in the chat if you don't remember them, and we can very briefly go over that. Now, a void pointer or void star, you'll hear the term used interchangeably. Um, a void star is a pointer that doesn't have a data type associated with it. Now, all pointers are just addresses in memory, but the type that is associated with any given pointer, an integer pointer or something like that, just allows the computer what to or it tells it what to do with certain operations. So we don't have that with a void star, um, but pthreads are perfectly fine with this, so we don't have to worry about it. The second big thing that you will notice is that it takes in void star as well as an argument. This can get a little bit frustrating, and we'll talk about why this is in 2 or 3 slides, I believe. But if you guys remember casting, casting from between data types, anything that you pass into this method that you want to use as an argument needs to be passed in as a single void star argument. So we'll go over how you do that in practicality later on. And then finally, to just create a pthread, no special conditions or anything, we do the pthread underscore create call, and there are 4 different arguments that go into this. This is on the next page. Yeah, so let's go to the next page, and we'll go over what each one of these are. Okay, so there are 4 parts to this. Of course, it returns an integer, which is simply the status of the thread or the status of the creation of the thread. So if it fails, it's going to return probably an error value, and I think it returns 1 if it's successful. You'd have to check me on that though. So let's go over the 4 parts of the 4 arguments that are passed into pthread underscore create. The first one is going to be a pthread underscore t argument. Now what this is we create a variable of the type pthread t. And this is defined in the pthread.h header file. And all this does is it just keeps track of where a pthread is. So any operation that we need to do to the pthread, like waiting for it to rejoin, or getting information out of it, anything like that, we will use this variable, this pthread underscore t variable, to get the data from it. Now it's passed in as a pointer, so the thread will, or the pthread underscore create will write all of this information back to the variable that we passed in, because it knows what the address is of it. Let's see. Next up, we have our attributes. I think for the level of stuff you guys get into, you don't actually have to do anything with the attributes, so we're just going to skip over this. It's basically special conditions or a special way that you need to set up a thread, and this can be discovered through documentation. So second up, we are passing a function, more specifically a function pointer, over to the thread or the pthread create to be created as a thread. Now, function pointers, I'm not going to get into all the casting and silliness you have to do here to do it. Just think of it as the name of the thread that you are calling. So if you have created, or if you have written a function that you're going to call as a new thread, and it has those conditions of returning a void star and taking in a void star, if you have both those things, you can put its name here, and if you cast it right, which you can look at an example for, it's pretty much exactly the same every single time you cast it. You can pass that in, and you can use that function to be created as a thread. And then finally, we have our void star arguments. Now, this is kind of odd, right? Because usually you pass in arguments as multiple things, right? So the question becomes, what if you want to pass in more than one thing for your arguments? So say you have more than one argument. Well, we can go over that shortly. Alyssa, could you go 2 slides forward, or one more? Yeah. Thank you. So the way that we pass multiple things in is using a struct. Now, a struct in C++ is simply a collection of variables that can all be referred to at the same time. So one kind of crude analogy is think of it as a class in Java, but it doesn't have any methods. It doesn't actually do anything. It's just a nice little way of packaging up a bunch of information. And this is useful for us because if we want to pass in multiple things, we can put all of those inside a struct, and we can pass that entire struct, we can cast it to a void star and pass that entire thing up to the function that we are creating the thread out of. So that's it's pretty straightforward. You have struct, the name of the struct, and then you have two curly brackets with all the variables declared like normal in between it. And then you end it with a semicolon. Now, if we hop back, if we look at the what's on the bottom right-hand side here, this is how you cast to a void star for this. So you take your structure, right, which is so we'll call it myargs a, and you can then you can fill in the values in the field by doing a and then using the dot operator and filling out the two argument fields. And then finally, you are going to convert it to a memory address by using the ampersand, right? We're looking on the right-hand side of the expression here. We cast this entire pointer, right? Because a memory address is a pointer. We cast it to a void star, and then that is what we're going to pass up to create our new thread. Does anyone have any questions here? Which section would you like me to repeat? The structures? Oh, the void star thing. Okay. So when we have our structure, and we can see this, the structure is being declared over on the left-hand side. Now, the structure has a name, right? My_args, and it has its fields within it. So we have one called arg1 and one called arg2. So we can create a structure, and the structure contains all these variables, but we also need to fill out what those variables are now. So you can see up on the top of the red text on the right-hand side, the myargs a, that creates the structure itself. And then for the next two lines, we go through and we fill out each of these fields. Now, once we've done this and we have our structure and we have the values that we want inside it, we have to turn this into a pointer. We then need to cast it to a void star, so a void pointer, and then that is the thing that gets passed up to the pthread create function, which creates our new thread. So if we work across on this bottom right-hand side statement one more time, we have ampersand a, which takes a and returns the memory address of a, right? So now we have a pointer to a. We cast that to a void star, so we take off its data type, and then this is the thing, the void star that points to our structure that gets passed to the pthread create function. Does that make sense, or do you want me to clarify anything?
I know we did skip a slide, the void star slide. Do you want me to go back to that, Thomas?
Oh, yes, probably. Thank you, Alyssa. Okay, so for the void star stuff, void star is simply a pointer. Are you guys good on pointers, or does anyone have any questions about that right now? Okay, so a little weak. Okay, we can go over it. So anytime we create a variable in a program, right? We have it's stored at some memory address. So if I create int a equals 5 or something like that, right? That is stored at a memory address inside the computer. Now, the pointer is simply a variable that stores the address of that other variable. So if we have a pointer to a, let's call it a pointer, create a variable like that, we can point it to a, and that means that a pointer will hold the memory address of where a is stored. So pointers usually have data types associated with them. So you can have an int star or a char star, and the star is just the thing that denotes that it's a memory address. Let me make that clear. A void star is simply one that does not have a type associated with it. And this is okay, right? This is the way it's supposed to be for working with pthreads. Does that clarify anything? Or let me see. We can go over casting. Just have structure pointers. This is a TA question. Do any of the TAs know if the can any of the TAs look at the question in the chat, please? No? Do we have any TAs here?
Myth, come save
Yeah,
us.
sorry. I'm not too sure. I'm looking through the modules right now. Which one is it? Early chapters 1 through 3. I don't think it will have, since we are doing it from modules 4. I'm not seeing anything like that. What about you guys? No? Okay, so it's safe to assume that it's not going to be there, but
Oh yeah,
I
Mohammed,
can.
and
Okay.
I'm not a TA. If you didn't realize, I'm from the tutoring center, so I'm just sort of filling in the gaps a little bit. So I may gloss over some stuff that or go over some stuff that you guys aren't going to have on the test, but I'm trying to stay as focused as possible.
Yeah, if there is anything, I will let you guys know on Campus Wire, and I'll let one of the TAs know in the other section as well to let you guys know as well.
Certainly. Okay. Sure. Mohammed, do you want to go over any other? Yeah, no problem. Do you want to go any other pointer stuff, or does that satisfy you for this? For sure. Okay. All right, Alyssa, could we move on, please?
All right, sure. I'm just going to read the question that they had in the chat just in case anybody watching the video has it. And the question was, will the test have structs and pointer related coding from earlier chapters 1 through 3? And our general consensus TAs and everybody here basically just said, no, don't worry about it.
And this will be updated. So I'm sure the TAs will check and get back to you guys on that.
Yep, definitely. All right, so on to our next topic for the test, data sharing. So we've learned that threads can share data. I'm pretty sure some of you have heard of the lawnmower example, where you had maybe like a different companies, each taking care of different parts of a lawn, where the lawn was your shared data, while the different companies performing tasks like mowing the lawn or washing windows or something. That's the different threads interacting with that shared data. And like I said, that lawn was the area of shared data. We call that a critical region. Now, multiple threads in a critical region without proper things we'll learn about later, or we'll go over, it can lead to problems. If you remember from assignments 5.1 and 5.2, without a proper mutual exclusion, we can have things like a shared variable like count. It will repeat itself or sometimes just not work properly and you won't get the correct values. And a race condition is when you have multiple threads ending up with different results. This can happen because the threads are executing at different times. So you might have a thread that increments a variable and then a new thread acts as the variable, but it's using the new incremented value instead of the original value. And then if you go to the next slide, here are our mutual exclusion principles. These are pretty important to remember. The first one is that no two threads can be in the same critical region at the same time, because as we've gone over before, it leads to problems with that shared data. And then the second thing is that no assumptions should be made about the hardware. So the number of cores in your processor, the speed at which your system can run, et cetera, et cetera. The third thing is that a thread or process that's not in the critical region, it should not prevent another thread or process from entering that same critical region. That just causes what we call busy waiting, and that's not something we want, especially if your system doesn't have a lot of resources. It can really slow down something like that. Our last thing is that no thread or process should have to wait forever to enter critical region. They should at some point be allowed to enter the critical region and run what they're supposed to do. And then if we go, our first way of achieving mutual exclusion is called strict alternation. So in strict alternation, the threads are going to take turns executing whatever is in the critical region. The problem with strict alternation, though, is busy waiting, because you have one thread waiting for the other thread to take its turn. Even if that other thread doesn't want to take its turn yet, the other thread still has to wait until the turn is taken. And if we go To the next slide, we can show an example in some code. So to use strict alternation, we have our while loop, while turn does not equal actual arg. This is what causes the thread that's not its turn yet. That causes it to wait right there. It's just constantly looping and taking up CPU cycles. Then the thread that's going through the critical region, once it finishes the code in there, it'll run into your if else statement that will change the turn. So then the other thread that was stuck waiting can finally enter the critical region again. Now we have more options other than strict alternation. The next slide shows us Peterson solution. Peterson solution's a bit better than strict alternation because the threads can indicate if they're interested in taking a turn or not. We do this through two different functions, enter region and a leave region. So inside of the enter region function, you have your variable turns, and you also have an array. In this case, we called it interested, and we set it equal to true for the thread that's entering the critical region. Then, but the problem is we still have busy waiting. As you can see, we have the while loop where the thread that's not taking its turn yet, it's still stuck in there looping and taking up CPU cycles. So it still causes busy waiting as well. And then on the next slide, we have an example of it in code as well. Or, oh, okay, never mind. It's not in there. We have mutexes is our last thing we can use. And this is probably the one that you'll be using the most, because the crucial difference between mutexes and our other options is that there is no busy waiting because you're not continuously checking the mutex. It's kind of similar to the enter and leave region, just without the busy waiting. And then after that, we have how we use the pthread mutexes. We have our pthread mutex lock and our pthread mutex unlock. The parameter that goes inside of these locks and unlocks is a pthread mutex t pointer, and then whatever the name of your mutex is. So if you remember from, I believe it was assignment 5.2, you would use the address of operator, the ampersand symbol, and then your mutex variable to input the memory location of your mutex. Okay, is that the line? Okay, so is there any questions before we get into the review questions on that, of what we've gone through? No? Okay. All right. Alyssa, are you gonna pull up the poll or should I do it?
Would you mind pulling up the poll? We're going to use
I
the
can-
same one over and
Alright.
over again, and then we'll just reset it.
Gotcha. Okay. Edit poll. All right, so our first question here is which of the following lines should be used at line 16? And our answer choices are different versions of the pthread mutex lock. The main difference that's going to be in it is the parameter that we're passing in. So let's see, we have choice 1, choice 2. Come on. All right. Let me relaunch the poll. All right, do you guys see the poll questions now? Okay, yeah, I got a answer in. Cool, cool. Okay. I'll give you guys about 10 more seconds just to make sure you got all the answers in. All right, I'm gonna end the poll now. All right, so if we could move on to the correct answer. One more slide, Alyssa. Yeah, there you go. Yep, so our correct answer is going to be D. like I said before, when we were reviewing the uses of the mutex lock and unlock, remember we're passing in the memory location of our mutex variable. So if you see, we are declaring a mutex variable called mutex, and then to pass in that memory location, we had to use the address of operator, which is the ampersand symbol. So D is going to be your correct answer. Okay, and then if we can move on to the second question. So our second question is, which of the following lines are we going to be using at line 20? And it should relaunch. Okay, I'll give you guys 10 more seconds. And the first question, okay, I'm just gonna end the poll right here. So Mohammed, in the first question, we're just using the pthread mutex lock. So we don't actually need to use a void star. The only thing that we're passing in is our mutex variable, which we do through using the address of operator, the ampersand. Does that answer your question? Yes, you will have to pass in a void star, but it's not going to be for the lock and unlock. I believe we used it in the pthread creates. Okay, and then for our results on question 2, yep, everyone got it right. It's going to be A. It's again the same thing as the lock statement. We did it in question 1. You're just passing in ampersand, the address of operator, and your mutex variable. And then on our next slide, we're seeing what it's like being used inside of a function. This one's called withdraw. So it's a basic banking, it seems to be a basic banking app or application. And we're having this function called withdraw that allows a customer or someone to withdraw money from our shared variable called account balance. So we have a lock before the thread can access account balance, and then an unlock to let the other thread take their turn. Yep. All right. So question 3, which of the following lines of code should be at line 51? Keep in mind that you're passing to the void star deposit function, not the withdraw. And, here is the whole. Give you guys a bit more time on this one. Give you guys let's say 15 more seconds. All right. So if you go on to the answer, it should be C. Yep. So in our pthread create, we have your thread ID, ampersand ID1, null for a second value, and then we're getting using the deposit function. So our third value that we pass in is going to be deposit. And then remember, for our last thing at pthread create, we're passing in a void star or a void pointer. Anyone have any question on this? I know we had about 50-50 that answered A or C. You got it? Okay. All right, cool. All right, so let's move on to question 4. So question 4, which of the following lines of code should be at line 55? And keep in mind that you're passing to a void star or void pointer function. I'll give you guys 15 more seconds. All right, we'll end it there. So most of you got it right. It's going to be answer D. And the reason it's going to be D is because we're going to be using your second thread, ID2. We're using the withdraw function. So withdraw is going to be there. And then again, our void star or pointer. Anyone have any questions on that? I know we had a couple that answered B and C. No? All right. Let's keep moving on then. All right, question 5. Which of the following lines of code should be at lines 57? Oh, how do we know that? Oh, can we go back to question 4? How do we know that we had to use withdraw? So we knew how to we had to use withdraw because of the parameter that we had. If you look at line 53, we were having a W. The W is for withdraw, and then up there at line 49 with the previous thing was D for deposit. Yep, no problem. Okay. All right, question 5. So which of the following lines of code should be at lines 57 and 58? I'll give you guys 15 more seconds. All right. So our correct answer is actually going to be A. And we're doing A because in our pthread join, we're not actually passing in the memory location with ampersand or the memory address of operator. We're just going to be putting in ID1 and ID2. And you can look at this up on the linux.die website that we've had to use to check the different terms. You're just going to be passing in the threads without any operators. Anyone have questions on this one? Okay. Looks like we don't have any. Let's just move on to 6. So which of the following lines of code should be at line 22? This is our producer consumer code right here. I'll give you all a bit more time on this one. Give you 25 more seconds. Let's just give it 30. All right. So our correct answer is actually going to be C. Now, if we take a look at this code, you should notice that at line 15, this is for the producer. So in our producer, when do we want it to wait? Do we want it to wait when our array is empty, or when our array is full, or buffer? Is our buffer full or empty? We want it to sleep when it's full, right? And the way to check that is, of course, by checking it against our variable n, because n is the size of our buffer. Does that make sense to everyone? Why it's C and not A or D? Yep. Okay, excellent. And I think we have a couple more questions after this. I think there's 8 in total. Yeah, okay. So number 7, which of the following lines of code should be at line 23? So we're piggybacking off of question 6 right here. Okay, I'll give you guys 30 more seconds. It's a bit tricky. Well, Alyssa, the recording is going to be available on Canvas, right? Uh, okay. No, I'm pretty sure it's going to be. Yeah, pretty sure it's going to be. If not, I'll make sure it's on there somehow. All right, I'll go ahead and end this poll right here. And if we can move on to the next slide, we should see that the correct answer is going to be B. Now, when you're looking at this, you can immediately rule out options C and D, because if you look at their parameters that they're passing in, they're not passing in the correct parameters. Remember, for the wait statement, you had to pass in your condition and a mutex, but C and D, they only pass in the condition instead of a mutex. So we can narrow it down to A and B. Now, A and B, if we're looking at our function again, remember, this is the producer. So the condition wait statement, the condition that we pass in, that's the condition that we want it to wake up when the other function signals it. So we want producer to wake up when the buffer is empty, right? Not full. Does that make sense to people, or? Yeah. So just about the weight, or just like the whole thing? Okay, yeah. So the condition weight, you have two things you're passing in. You're passing your condition and you're passing in the mutex. Mutex, there's only one mutex here, so that's easily solved. Now the condition that we're passing in. So for this one, this is the producer function, right? So the producer, we want it to go ahead and wait or fall asleep when the buffer is full, right? There's no extra space for new things to be produced. Now, the condition that you're passing in to the wait, that's going to be the condition it responds to when you have a signal in the other process or function, sorry. So there's a producer function and then there's a consumer function. Inside of the consumer function, you have a pthread cond signal, and it will signal whatever parameter is in there. And the wait function, that's telling you which function or which parameter it's going to wake up to. So the producer, if you look at the wait statement, it's going to wake up when the condition not full is signaled. Does that make sense? So pthread condition. So the question is, so the pthread condition wait function puts the producer to sleep until the and not full condition is fulfilled.
Oh, Himeth, I would also add on that you guys can unmute yourselves and talk if it's
Yes,
easier.
yes. So yeah, it puts wait puts the producer to sleep. It puts the yeah, exactly. It puts the producer to sleep until not full is fulfilled. Yes. Do we have any other questions, or did that make sense to everybody? This is a bit tricky. There's definitely going to be producer and consumer. So if you have a question, what exactly is a shared buffer? So the buffer is just an array. If you remember from our, I believe it's assignment 6.1, you had your process order and take orders. You can think of that order array as this buffer we have here. It's just a shared, it's a global array that both threads can access, and it's just exactly what it is. It's just an array where the producer can input things and the consumer can take things out of. Do we have any other questions? This is what the input. So the question is this what the input and output stream of C in and C out are? Not, don't think so. Thomas, do you?
Yes. So these are not the same things. So a shared buffer is just a piece of memory that is shared between multiple processes. So if you have two threads and say one's reading and one's writing, or one puts something in to be processed, and the other one pulls it out as it is being processed, that is a shared buffer. C-in and C-out are streams, and they allow input and output to the program. Streams are a little bit of an abstract concept. And there are actually concurrency issues with streams. For example, two threads trying to print out at the same time, but the issue generally isn't sharing memory itself in the programming sense. Does that help at all?
Gotcha. And you can always ask some more questions on either in this review stream or on Campus Wire or email, the TAs or professors. So make sure you get those answers in, because there is going to be a producer and consumer stuff on the test. So, all right. If got no other questions, I'll move on to the next question we have, or next review question. And no, there will be producer and consumer. There will be. Yep. All right, so question 8. Which of the following lines of code should be at line 34? Let me just relaunch the poll right here. I'll give you all about 30 more seconds. Okay. All right, excellent. So everyone that answered, you got it all. You got it correct. Yep, your answer is going to be C. You're going to be signaling not empty, so that the consumer can wake up or stop waiting. Any additional questions? I think this is the last of the data sharing review questions. Yeah. Any further questions? And this is just the example of the consumer, and then what the main, or yeah, what the main looks like. Okay, I think there's no other questions. Excellent. So in addition to the shared data, we also have decomposition types. And that's just the different ways you can divide the work among threads and processes. So we have two of them. One's data decomposition and task decomposition. So in data decomposition, you have different threads or processes executing the same function on different data. So if we think back to that lawnmower, or lawnmower analogy, imagine you have, say, 4 different lawns, and you have different companies just mowing that lawn. You're doing different threads are doing the same function on different pieces of data. In task decomposition, you're having different threads and processes execute different functions. So instead of all 4 companies mowing their lawn, one mows the lawn, one paves the driveway, one washes your windows, something like that. And then there's another option, a third one called data flow decomposition. We have one thread executes a function and produces output data, and then the other thread executes a different function and consumes data. Anybody, any questions on that? What does the consumer do when it actually removes information from the buffer? So it depends on what the code is inside of that consumer function. Let's say in your assignment 6.1, you have the process orders. It removes the order from that order array, and then it prints out a statement like processing order, and then or order confirmed, and then processing order. So it's going to be, it depends on what exactly is inside of that consumer function. Yeah. Any other questions? So the consumer works once the producer has put information in the buffer because there's information available to use. Exactly, yep. If you remember from our producer consumer example, the consumer actually has to wait or falls asleep if there's nothing inside of that buffer. It has to be signaled by the producer that there's finally something in the buffer for it to start working again. Good questions, good questions. Any other questions here? And how exactly does this avoid busy waiting? So in our producer and consumer, I'm assuming that that's what you're talking about. Remember, we're using mutexes, and it's the mutexes that have the advantage of not having busy waiting. The busy waiting is when it's waiting but taking up CPU cycles. So that while loop, it's constantly checking the status. But in our producer consumer, we're just putting them, or we're just having them wait or put to sleep so they don't take up CPU cycles and they'll just wait for a signal. Any other questions? Okay. I think that's all the questions we have. Excellent questions. All right, Alyssa, to you.
All right, on to CPU scheduling. So first, what is?
Hold on. I think we just had another question. So are not empty and not full. So not empty and not full aren't mutexes. Those are conditions. If you remember, you declare them as pthread condition pthread underscore cond underscore t, and then you initialize it if you're using the macros to pthread underscore cond underscore initializer. Yep. Yep. All right. Cool. Yeah. Sorry about that, Alyssa.
No problem. And we're back. So what is CPU scheduling? So computers run a lot of things at the same time, but every CPU can only run one thing at a time. And every program then has to have its turn on the CPU. And what's running on the CPU changes really fast. And the system uses what's called a scheduler to help it figure out what program gets its turn on the CPU at what time. And the scheduler will wake up and put to sleep programs based on which one is running and which one's turn it is. There are a couple different CPU scheduling policies that you've probably seen so far. The first one being first come, first serve, which is the simplest one. It basically just says that if you arrived first, then you go first, and it uses a queue to track that. Next, we have shortest remaining time first. which works with a special queue called a priority queue. And it works like a normal queue, except it has a condition. This condition is that if it has a lower remaining time in the queue, then it hops up in the queue, it gets to cut the line. And this happens even if a job arrives in the middle of a currently running process. So let's say you have a job with a running time of 5, and in the middle of that 5-unit time running time, another process arrives with a lower remaining time. It'll just cut off whatever's running and then take its place and continue carrying on. And last but not least, we have round robin. And round robin uses another special type of queue called an enhanced queue, and it uses something called a quantum. And a quantum basically just tells the process how much time it can go. So it has a set amount of time to run. So even if a process has a total burst time of 4 or 5 or some large number, it can only go as long as the quantum says it can go. And if a process goes through a quantum without finishing, it'll just go to the end of the queue. So if it doesn't reach that quantum amount, so let's say you have a quantum of 2, but the next process that's up in line only has 1 time unit left, it'll just run whatever it has left, and that's okay. And lastly, to note, input-output wait time takes the process out of the queue until it's over. So that's like a cooldown. And that's something we'll talk about in our example on the next coming slides. So here is our CPU scheduling example. Don't rush to write this down. It'll actually be on the next couple slides as we go over the example. And the best way to practice these problems is to do them repeatedly. And in my opinion, it's equally as important to practice inputting them into Canvas as it is to learn how to actually solve the problem, because the Canvas can be a little wonky sometimes, and just making sure you have the right thing in the right place is very important. On this slide, we have a handy little doodle of a way that you can visualize this for yourself. It's a graph. A couple things on this graph. We note that each process has a given 2 quantum, meaning that they can only burst up to 2 units of time at a time. And we're going to be using round robin for this. So we do have the quantums. I went ahead and put the arrival times of our jobs up there in the x-axis. And the x-axis just has units of time from 0 to 24. And the y-axis is where we're going to keep track of each of our jobs. And last but not least, on the bottom left, we'll have our queue. So to get started, at time 0, we have D. Down here, D enters the queue, and it starts with a burst time of 5. We go ahead and run it. It bursts for 2. D goes to the end of the queue. It started with a 5, but since it bursted off 2, it's now at 3. We have something in the chat. And the question is wait. So for round robin, the processes and the order in which the processes arrives matters. So yes, the order in which the processes arrive do matter. It matters for everyone except for the one with a priority queue, where if it has a lower time, it jumps to the front. So D arrived first at arrival time 0, so it goes on first. And then while D was running, B arrived at time 1. So B goes on while D is running, and then D doesn't come back until time 2, which is why D goes to the bottom. Does that make sense? And then you said, I thought all were considered equally important according to the lecture video. So when I say arrival time is taken into consideration, I don't mean that it cuts to the front of the queue. I mean that D being at time 0 means that it goes on to the queue first. So when you're starting, the arrival time is taken into consideration. So their starting points are taken into the consideration, but once they go onto the queue, they don't skip or anything. They just get stacked onto the back. All right, cool. Glad I could answer your question. So going back, we have D bursted, D went to the back, and then B hopped on while D was running. So now we're here. Process B is at the top of the queue, so we'll go immediately after process D. So now process B, it's its turn to shine. We go ahead and pop 2 off. So B has run 2, but a lot has happened in this time. B just ran for its 2 quantum burst. And during that time, D moved to the top, which is normal. C moved right under D. And now our problem is that A arrived at the same time as B is returning. So then this question is, which one goes first, B or A in the queue? And I'm actually going to go ahead and pop a poll for you guys. And it's going to be, what do you think the order is going to be? Is B going to go first into the queue because it's returning? Or is A going to go first into the queue because it's arriving? All right, I'm going to go ahead and end the poll there. And if you read the tiebreaker, it actually says if a process finishes its quantum at the same time as newly arriving processes, place the process that just finished its quantum before the newly arriving process. So that means if you picked B, then you were correct. So B was a returning process, but A is a newly arriving process, so B has priority. And the reason why this wasn't a problem for C is because C arrived in the middle of the process, not at the end. It arriving at the end, A arriving at the same time as B, was where the conflict came from. So let me check the chat. No questions yet? All right, awesome. So I will carry on. So here we are with the same alignment as before, and now we're popping off D. So D is still at the top of the queue. D pops off for its 2 quantum burst. And here it is ending at time 6. So now the queue looks like this. C shifted up, B shifted up, A shifted up, and D went to the back. 3 minus 2 is 1, so now D is stuck at 1. So now C is next. And C only has 1 burst left, and that's okay. And Mohammed said, so this is similar to exercise 6-2. I'd imagine it is. I'm not familiar with the exercises, but you're free to go back and compare them. So C is now at the top of the queue, and it goes next. So here we are. It pops off with its 1 burst, and even though it's less than the quantum of 2, that's okay. For round robin, it's okay if something has less than the quantum number, it can still finish. And because C only had a total CPU burst time of 1, C is completely done. It's out of the problem now. Now our queue only has B, A, and D left in it. So we did the same thing as before. We shifted B up, we shifted A up, we shifted D up, and now it's B's turn. So we go ahead and use the final 2 bursts in B. But B is a little special. B has a burst time, then an input-output wait time, and then it comes back in the game to finish up. So denoted here with the gray boxes are its cooldown time, its input-output wait time, which means that it basically just gets taken out of everything, and then it re-arrives after it's done cooling down. So that's why its new arrival time is 11. And we have a question that's saying, wait, could you explain how you placed in D starting at time 4? So if we rewind a little bit, D over here, B ran at time 2. And while it was running, D shifted to the top. And then while B was running, C also shifted into the queue. So while B is running, it doesn't hold its place in the queue. Things continue to shift up while B is running, which is why D automatically went to the top as soon as B started running. And then C automatically fell in behind it as soon as B was starting to run. Because B leaves the queue and then it has to re-enter the queue after it's done with its burst. And that's why when it was returning, there was a conflict because A was also entering at the same time. It was arriving at the same time as B was re-entering the queue. And then from there, we carried on and we popped off D here. Everything shifted up again. We popped off C here. C was done. We shifted up again. And we just popped off B, which triggered its wait time. Does that make sense? Did that answer your question? Awesome. So I'm glad I could help. You can think of whenever a job leaves the queue and starts running, it just loses its place, which is why it ends up at the bottom. So back to our cycle. B is running, it has its wait time, it has a new arrival time. So what happens next? Now it's just A and D while we're waiting for B to cool down. So A would go next. A would use its last two quantums, well, a quantum of 2, but then it would use its last 2 burst times. And then it's also like B, it has an input output wait time of 4 before it comes back. So we'll do the same thing as B. We log down the input output wait time, and then we mark where the new arrival time is. So what's left? D is still left, it shifts up. And then by the time we're at 11, where A finished off right here, B came back because it was done cooling down. And because it's arriving, it goes to the back. So now D only has 1 left. So we went ahead next and popped off its last burst time. And now we're here. D is completely done. C is completely done. We're waiting for A to be done cooling off. And now we just have B. So at time 12, we use B because it's the only thing in the queue. So we pop off the next 2 burst times and we get to time 14. And at time 14, A isn't ready yet. So B gets to go again because there's nothing else in the queue. It uses up its remaining 1 burst time, which brings us to 15. B is completely done, which leaves A. From this point, A pops off. It uses its 2 quantum burst. And because there's still nothing left in the queue, it does the same thing and it uses its final 2 bursts. And then from there, the problem is over. All of the bursts have been used from jobs A through D. I know that's a lot. Do you guys have any more questions? All right, I'm going to check the chat. Nothing's in the chat. It's okay to ask questions, guys. All right, in that case, that actually concludes our review session for you guys. And if Thomas, Hemoth, if you guys have anything else to add, now would be the time to do it. If you guys in the chat have any more questions, or if even if somebody just wants me to run through this again for like a minute, the process behind the queues, moving things up, moving things back, the tiebreaker is really important.
No, I don't have anything to add unless anyone has any questions about concurrency, pthreads, anything of that nature.
Yep, pretty much the same as Thomas. As long as you don't have any questions on data sharing, I think we're good to go.
All right, guys. Oh,
Oh.
we have a rerun through
Oh.
round robin CPU scheduling. I got you. I got you. Okay, so let's go back and let us backtrack through this guy all the way back, and we'll just speed run, and then you can unmute your microphone or pop something in the chat. So here are the scheduling policies. First come, first serve means you come in first, you go first. Shortest time remaining is the special one that lets jobs cut in line. So if it enters the queue, but it has a lower remaining time than everything else or something else in the queue, it can jump the line. And then here's what we're using for the problem, which is round robin, which is exactly like first come, first serve, except each process can only go for a certain period of time. It's capped by a quantum. So instead of being able to run its full burst, it can only go a certain number at a time. So like in our example, that is 2. Here's the job description, and here's where we start. So we start quantum of 2. Here are our jobs, description of round robin, and the queue starts with D because D has the first arrival time. So here are the examples of what's on the graph. And here is D. So D gets put in the queue. It arrives at 0. Our quantum is 2, so it has a burst time of 2. It started with a total burst time of 5, and it needs to expend all of its bursts to get to the end. And after expending 2, it goes to the end of the queue, and it has 3. During the time that D was running, B arrived at time 1. B went to the top of the queue while D was running, and it has a starting burst time of 4. D went to the back of the queue, and now it's B's turn. So B, here it ran for 2. And while B was running, D shifted up. C went right after because it joined while B was running. And then A arrived at the same time as B was supposed to return. And that's when we had the tiebreaker, and we said if something finishes its quantum at the same time as newly arriving processes, place the process that just finished its quantum before the newly arriving process. So B had just finished its quantum. It's not newly arriving, it's returning. So if it's returning, it goes first. It has priority, which is why we said B goes first and then A. D is at the top of the queue. So here we're just popping off 2 off of D like that. And then we did the same sort of process where C shifted up, B shifted up, A shifted up, and D went to the bottom and expended 2 more. So 3 minus 2 is 1. That's why D has 1 left. Next, we have C, which has a small burst time of 1. So we go ahead and expend that. And we do the same thing. We shift B up, we shift A up, we shift D up. C is completely knocked out at this point. Now it's B's turn. But this time, when B pops off its next 2 quantum, it has an input-output wait time down here. So popped off this 4, now has to cool down for 2 before finishing with 3, which is why it's on the bench here waiting, and then its new arrival time is here. So it'll re-enter the queue at that point. Here, we're just showing that we're shifting up A and D now that B's done and waiting. And then we should go ahead and pop off 2 for A. So A uses its 2 quantums here. And we're going to pause. We have a question. So somebody asks, oh, so the input output wait time happens upon the completion of the job? Yes. So you can think of input output wait time as this is the first section of the job. This is how long it has to wait because it's expended itself. And then it comes back in the game at this time. So these burst times do have to finish. It's just that there's a break in between. That's what that when input output wait time means. And that's why we have the gray boxes here. So for B, it had 4 bursts here. 1, 2, 3, 4. That's this first section. Then it has an input output wait time. So once it's expended these 4, it has to wait 2 blocks of waiting before it can finish out with the last 3. And it doesn't come back until time 11. And during the time that it's waiting, Going back into the problem, we shifted A up and we shifted D up. So now A can go ahead and continue. And the same thing happens in the next slide when A went ahead and expended its first 2. So A had a first half CPU burst time of 2. So 1, 2. After it's done with those, it had an input output wait time of 4, which is why it has to wait 4 until it can come back in the game and finish up the last 4. At this point in the queue, D shifts up. And then B is there. It's able to return because it's done cooling down. And then D expends its very last burst that it has. And then we shift B up. B goes ahead and uses the next 2 quantum. And it's the only thing in the queue after it's done with that next 2. And it only has 1 left. And it uses it. Luckily, at that point, A is back by 15. Its wait is over. And its remaining time, if you look down here, is 4, which is why A is 4 here. We use next 2 for the quantum. We burst it out. And then we do the same thing. And at that point, the problem is finished because all of the bursts have been used. And I'm going to go ahead and check the chat for questions. And we have a question that asks, so even if the job doesn't take the whole quantum, the CPU just moves on to the next job? So my answer to that is yes. The only time it doesn't take the whole quantum is when it doesn't have anything else left to give. So for example, C only ever had 1 burst time. So it never had more than 1 burst time to give. And for round robin, that's okay. The quantum says that you can use a maximum of 2, but if it uses less than 2, that's okay. So when C finished off here, that was okay. And then when B finished off, or D finished off here, because that was all it had left, that was okay as well. And then, like you asked in your question, yes, it would just carry on with the algorithm. Does that make sense? Oh, okay. So the chat says that they thought scheduling jobs under round robin meant it had to match to let the whole quantum run through before rescheduling. So no, you do not have to. You can finish off what you have left. All right, I'm glad that makes more sense. So I'm going to go ahead and stop sharing for now. And if Hemoth, Thomas, do you guys have anything else again?
No.
Nope.
Looks good. Best of luck to all of you on your exam.
And again, if any more questions, just reach out to us, Campus Wire, email, ask us in class. We're here to help you.